Hello! Last time we have learned how to perform offload to one coprocessor and to multiple coprocessors. Next, in this episode 3.7, we'll look at how to overlap communication of data with computation on the coprocessor and CPU at the same time in the explicit offload model. For that, we will use functionality called asynchronous offload.
Another term for it is non-blocking offload. Our application will start the offload and continue with the execution of the rest of the instructions until a synchronization point. This way, the host can do additional computation or data movement while it is waiting for the result from the coprocessor. We will be using the matrix vector multiplication application as an example again. The source code has been slightly modified. Now there are two output arrays, chost, which holds the result from the host, and ctarget, which holds the result from the coprocessor. The two results are compared at the end to verify that our application is correct. Let's begin by implementing memory retention as we learned several episodes ago. And now we will offload one instance of the matrix vector multiplication function to the coprocessor. Done. As of right now, the code is ready to perform standard blocking offload. Now let's make this offload asynchronous. To do that, in the offload pragma, we add the clause signal. The argument to the clause signal must be a pointer. This pointer will be used to identify the specific offload code because we can have many of them during synchronization. Note that we are specifying the coprocessor, in this case coprocessor number 0, in the target clause. This is so that we do not have a case where we offload asynchronously to one coprocessor, then wait for results to come back from another coprocessor. Before we print the result, we must make sure that offload has completed. In other words, we need a synchronization point. To synchronize the offloaded processes with the host application, we have to use the pragma offload wait. In this pragma, we specify that we are waiting for offload on coprocessor number 0, and that we are waiting for offload identified by the same signal pointer as we used in the offload pragma. Now let's compile and run the application. The errors you see are due to the makefile trying to cross-compile for the make architecture or offloading code. Those two programming models should not be mixed. If you don't know why, please refer to the episode 3.1 overview of programming options. Make run CPU will run the application on the host. We can see that the results are correct. A common pitfall of asynchronous offload is forgetting to synchronize. Without synchronization, the host may start operations that are dependent on the result from the coprocessor, in our case the verification. To demonstrate this, let us comment out the synchronization pragma in our example code. When we compile and run the code, we see that the application produces an incorrect result. Thus, remember to always protect against this issue by synchronizing before using any results of asynchronous offload. Finally, let us try to offload to multiple coprocessors. The index in the target clause of pragma offload can be used to offload to a specific coprocessor. This code snippet will offload calculate to each coprocessor in order. However, recall that the offload is blocking, so this code will be executed sequentially on coprocessors. To offload to multiple coprocessors simultaneously, there are two approaches, the asynchronous approach and the multithreaded approach. In the asynchronous approach, we use the clause signal, discussed earlier, to make the offload non-blocking. Be sure to assign different signals to each instance of offload and to wait for all offloads. The advantage of this approach is that only one thread on the host can manage all coprocessors. However, the disadvantage is that the offload bandwidth will be limited by the memory bandwidth of a single memory controller. There is another way to perform offload to multiple coprocessors. It uses multiple threads on the host, each handling its respective coprocessor. In this code snippet, we have used a parallel framework called OpenMP to create threads. Do not worry if you are not familiar with OpenMP or multithreading, because those topics will be discussed in depth in a later video. The important concept to understand here is that the line pragma OMP parallel spawned multiple threads on the host CPU, and each thread executed the code in the scope of the pragma. In our code, each thread performs offload to the coprocessor corresponding to the thread number. At the end of the parallel scope, there is implicit synchronization between threads. The advantage of this approach is that the total bandwidth scales with the number of threads. However, the disadvantage is that this approach takes up multiple threads. Multithreading approach is often used for load balancing.
Thank you for tuning in. In the next episode, we will talk about specifics of heterogeneous programming using MPI, how to distribute work across multiple coprocessors, and what communication modes can be used for that. Once again, thank you, and I hope to see you in the next episode.